over this very quickly. It's worth seeing again. Take y equals x squared table and invert it to get the inverse relation. It's not a function because it's not one-to-one. X equals 4 gives you -2 here, but it gives you 2 here. You don't have just one answer for what happens when x equals 4. If we restrict the domain from 0, including 0, and then numbers greater than 0, so the restricted domain for this discrete function would be 0, 1, 2. Then the corresponding part of the inverse relation becomes a function because it's now one-to-one. If we take the f of x equals x squared function, the complete y equals x squared function, we would restrict the domain to 0, infinity for similar reasons. If this thing just keeps going, we still want to use only positive values, so we have a one-to-one function. The inverse relation becomes f inverse of x equals x because why? Because inverting y equals x squared for x greater than or equal to 0 gives us, among other things, positive values of y, but we have to use positive values of x. So we have then x equals y squared. If we solve for y, then since x has to be positive, we get y equals plus or minus the square root of x. But since the y values all have to be positive because x squared is always positive, we get y equals the square root of x. We only get the plus. And that's our inverse function. So that's why f of inverse of x equals 1. We also had the example of the basic exponential function, and we haven't gotten in the text to exponential and logarithmic functions, but we want to understand this in the same scheme because it'll make it much easier when we get to the next chapter, which is coming up pretty soon, right after break. Okay, so we do the y equals 2 to the x. We note that this is one-to-one. We reverse the columns, and we've done this. I'm doing this quickly. And we get the inverse function, which is a log base 2 of x function. The graph of the inverse function is here because the graph of the exponential function is here for reasons that we've talked about. So that's a little introduction to what we do with inverse functions. So now we get to having to use some algebra to invert other functions. And I want to stay fairly close to the examples you're going to have to do for homework, especially since we have to quit in a little bit early today. Okay, so f of x equals x plus 3 squared. We can see just by the graph that this graph will be the x squared graph will be shifted 3 units to the left. So here's our graph. It's very badly drawn, but we still get the idea. And we have to restrict our domain here so that we pass the horizontal line test and it's one-to-one function. So it's -3 infinity, and it's a closed interval on this end because it includes -3. Just looking at this, if x is less than -3, well, I'm going to stick with this. Okay. This is why we restrict the domain. Okay. We'll see another reason. Okay, y equals x plus 3 quantity squared defines f of x. So x equals y plus 3 quantity squared. Now remember that your x values had to be positive. Then this function gives, first of all, y squared plus 6y plus 9 equals x, and I don't want to do it that way. It would involve the quadratic formula and more algebra than necessary. The easier way to solve this is to say that, okay, well then y plus 3 okay, because if a square equals something, the square of a quantity equals something, then that quantity is plus or minus the square root of that something. To do the square root, x can't be negative, so x has to be greater than or equal to 0. So y has to be 3 plus or minus the square root of x. But remember that y has to be greater than or equal to 0. Okay, well, and for some reason, okay, well, if 3 plus x is greater than or equal to 0, then square root of x is greater than or equal to -3, but it always is greater than or equal to -3 because the square root of x is greater than 0. So this is always so. So x has to be greater than or equal to 9. So that now F inverse of x equals 3 minus the square root of x with x greater than or equal to 9. So there's some complications here. We have to consider them. Part of the definition your text uses and is generally used you understand that we could also restrict the domain to the left-hand side of this parabola. Okay, so that now the function would still be 1-to-1, but then we'd have to have some negative values. I don't want to go into that just for time. On this side, the function is decreasing, and we want the function, in this case, to be non-decreasing. So we have to choose this side. Okay, so this is if it's non-decreasing. There's a problem with that in that if we always want the inverse to be non-decreasing, that kind of messes up what happens if we try to inverse the basic reciprocal square function. And we really want to inverse that on the interval where it is decreasing. But that's a definition that your book wants to use at this point. Okay. Now, another example would be, for example, f of x equal four plus the square root of x. If we switch x and y, of course, we could write this as y equals 4 plus square root of x. We get x equals 4 plus the square root of y. And we note that y has to be greater than or equal to 0. Solving for y, we get x minus 4 equals the square root of y. So that y equals x minus 4 quantity squared. Now, x minus 4 quantity squared is always greater than or equal to 0. So y is automatically greater than or equal to 0. But there's our function. Now there's a test for inverse functions. That is that f applied to f inverse of x should equal x. Well, in this case, f of f inverse of x equals, okay, to do f of f inverse of x, we replace x up here with f inverse of x. So that would be 4 plus square root of f inverse of x. And that's 4 plus square root of quantity x minus 4 squared. Which is 4 plus the quantity x minus 4. And I'm being a little bit careless with that because the square root of x minus 4 squared has to be positive. So I'm going to make that an absolute value. And this equals x if x is greater than or equal to 4. So this is the inverse function as long as you restrict the domain to x being greater than or equal to 4. Now, the big key on this section, the first thing you got to be able to do is you got to be able to do the algebra to invert these things. So we're just going to run through a couple more and do the algebra and not worry too much about domain and range, but that is something that you need to pay attention to. Suppose you have f of x equals x plus 4 over x minus 2. You know what the graph of this looks like. It's going to be a rational function, horizontal asymptote at x equals 1. And, before I do this one, I said something over here that's wrong. I said the degree of the numerator equals the degree of the denominator because it has horizontal asymptote at the x-axis. It should have been less than or equal to the degree of the denominator. So the degree of the numerator equals the degree of the denominator. Then you don't get a horizontal asymptote at 0. So make sure you understand that part of the reasoning. I wrote that down carelessly. Okay, so you have y equals x plus 4 over x minus 2. Your inverse relation would be x equals y plus 4 over y minus 2. You're going to have to restrict your domain on this function. Now, the graph of this function can have a vertical asymptote at x equals 2, horizontal at 0 at x equals negative 4. It's going to approach x equals plus 1 at both extremes. So the graph is going to look like this. This is an example of a function where you can't have a domain where the function is increasing. So we restrict the domain here. And the inverse relation has to be x greater than or equal to 2. We could invert it here also, but we're going to use the one where the values tend to be positive. So we're going to do this. So x is going to be y plus 4 over y minus 2. We're going to solve for y. And this is a little more complicated to solve for y. We multiply both sides by y minus 2, and we get x times y minus 2 equals y plus 4. Okay, well then, we expand over here, we get xy minus 2x equals y plus 4. Now remember, we're trying to solve for y. So we subtract this y from both sides, and we add 2x to both sides. Subtracting y from both sides, y goes away here, appears over here as negative y. So we get xy minus y. Then we add 2x to both sides, which will give us 0 over here. 2x goes away and appears over here. The y went away, so we end up with 2x plus 4 on this side. And now we can solve for y. Because we've got all our y's on one side, we can factor out the y. And we get y times x minus 1 equals 2x plus 4. And then we divide both sides by x minus 1. And there we have it. So f inverse of x equals 2x plus 4 over x minus 1. So the algebra here is a little more involved than it has been. So you might want to think about exactly why we do every one of these steps. And then we can verify that this is an inverse relation. Now, among other things, for this function, we note that y is greater than or equal to 1. This line here is x equal 1. So y is always greater than, not even greater than or equal to, it's greater than 1. Okay. When we invert, now it becomes x greater than 1. And that was on the original restricted domain. So here's our inverse function. And clearly, it's good that x has to be greater than 1, can't be equal to 1, because if it was equal to 1, you'd have a 0 in the denominator here. Since x is greater than 1, x minus 1 is always positive, and 2x plus 4 is always positive. So the inverse function is always positive, which has to be the case if you invert this curve. We'll note f of f inverse of x equals what? Equals, well, replace x by f inverse of x. You're going to have f inverse of x up here wherever you have x. We get this. Now, of course, f inverse of x is this divided by thought I'd left something out there. Had to convince myself that I hadn't. Divided by this. Well, if you simplify this, it comes out as x. I'm not going to go through all the details of this simplification. I'm just going to say that, well, you then multiply the 4 by x minus 1 over x minus 1, so you have a common denominator here. And you do the same down here, so you have a common denominator. Then,
shouldn't the denominator be -2 in the very end? You have -1 right now. Yep.
yeah, that doesn't affect the greatest common denominator, but it sure affects the accuracy. Okay. Yeah. Okay. Thank you. So doing this, then putting this over common denominator, this over common denominator, we then invert this and multiply by this. Your x minus 1s go away, and the rest of it all comes down to x. So I'm not going to do that algebra just because of time. A couple more examples that I want to get to. But you have a couple of examples of functions of this nature that you want to invert. Okay, well, that's the process, and that's the overview. And I am going to want to go ahead and stop at this point. We're stopping about almost 15 minutes early. And I apologize for that, but I do need to get that driver's license renewed. Notice that I've got DMV written on my hand 4 times, so I don't forget, because I did have an appointment back in November and I was so busy with my class I forgot. Okay. So there we have it. That's an overview. I think you'll be okay with it. Some of the application problems might raise questions, but they're usually pretty straightforward. And I don't want to try to give you a variety of application problems at this point. I'll let you get the mechanics of the process down because I think you're going to understand that. So, do you have any questions at this point?
No, I don't.
Okay. Well, I think you're in good shape. And as I say, the work that you sent me looks quite good. I'll go over it in detail and just see if there's anything wrong in there. It looks like your approach is correct on every problem. So if you missed anything, it looks like it's just details of the kind that I keep missing. You're watching me too much, so stop doing that.
Yeah.
Okay.
All right.
And let's see, we have scheduled part 2 of your test. Is that for Monday?
Yes.
Yeah. Okay. And that is scheduled. Have you taken a look to make sure it's really there?
Well, it's blocked right now. I cannot.
It's blocked, but if it's there and says it's going to open at 11 o'clock, or it was 10 o'clock, wasn't it?
It was 11.
Okay, 11 o'clock on Monday. Somebody scheduled something for 10 o'clock, but it wasn't you, I guess. Yeah, if it says it's scheduled, I've already double checked the link.
All right.
As long as I don't do anything completely stupid like, erase the file, and I never do that sort of thing. It should be there on Monday. So good luck on the exam. I'm confident that you're going to do well. Some of the problems are pretty challenging. So you probably don't need quite 90% to make an A. Usually 85% is an A. 70 is a B, 55 is a C, and even 40 is a D, because if you can do any of it, you know something. So fairly challenging test. Look forward to seeing your work because I think it's going to be very good.
We'll see. Thank you.
Okay.
And we'll see you after the spring break.
Yes.
All right.
Very good. Email me if you have questions in the meantime.
Will do. Good luck at the DMV.
Not a matter of luck, just a matter of showing up and hoping they don't throw me into jail for being this late. And I think I've got some pretty good excuses, but we'll see what they do. I might even end up with a fine or something, which I'll be glad to pay. Okay. I think COVID is a pretty good excuse, though.
Yeah.
Okay. So
right.
you take care. See you in a couple of weeks, if not before.
Okay. Take care too. Bye-bye.
Bye-bye.